Okay, Assalamualaikum. And I would like to apologize for the last week because I'm not feeling very well. And almost 2 weeks, I'm not feeling very well. And due to the fever and also I have a sore throat. It's very bad for this one. And Alhamdulillah, I'm getting better. And this evening, I would like to give some briefing regarding the lab sessions for the past last weeks and regarding the greedy algorithms. Okay, and I know that Dr. Suranti already gave you some lecture regarding the new topic, finite state machines, and also greedy algorithm. And I think that it's not too late for us to do the lab session for the greedy algorithm. And I, Dr. Suranti already given a very step-by-step instruction regarding the grid algorithms, spanning tree, and also the Huffman coding. Okay, so this evening, I just want to give some briefing and some tips in order to how you can solve the question for the lab exercise. Okay, I will let you to download the document from the model, okay, from the column. And this one is the exercise that you need to submit within 2-3 days. Okay, so based on the question that we have here, so this is a Huffman coding. All right, so hopefully you still understand about the Huffman coding here and the purpose of this algorithm for the data compressions, data encoding, and what else? Image compression and so on. So this is the algorithm that you need to understand how the process of this algorithm being done or execute. All right. So example of the left exercise here is given like a pattern. Okay, a message, right? And just example for it, how we can encode this message into encoded versions, right? So what the meaning of the encoded here is we want to reduce the number of bits instead of we keep the original of the bits in during the especially for the network transitions, okay, compression and so on, because this is very important if you want to uh, transfer a file, right? Instead of we are transferring the original size of the file, we can encode it, we can reduce the size of the file for better transmissions. Okay, so this is the purpose of the algorithm itself, right? Okay, so you need to understand how the process is done. Okay, so using the Huffman code, show the process of encode the message, calculate the message size of this message. Okay, so based on the instructions given by the Dr. Serenity, there are several steps that you need to do. Okay, so I think they are just to give some briefing again this one. And the first step that you need to do is try to identify the unique X key symbols or X key character in this message. All right, okay, so that will be the first step that you need to do, and then you need to count the frequency of the unique ASCII code. All right, for example, here we have a G, F, A, C, D, E, and also what else? And also B. All right, so you need to count numbers of S key that is unique. What do you mean unique here is only once, right? Even though we have a multiple of the same S key code, let's say for example F here we have 2 F S key code, right? So the unique is only F. Okay, so then you need to write down the code for it. Okay, and then you need to count the unique character from the message here. All right, so I want to share a screen from my tablet here. Okay, can you see my screen here?
Yes, sir.
And this, yes, okay. So my screen here is from my tablet here because I want to do some drawing, okay, for your better understanding. And as just mentioned just now is you need to identify the unique ASCII character here. Can you count how many unique ASCII here? Okay, we have you can try to follow me. We have G. Okay, we have G. What else we have here? We have F. We have A. Okay, what else we have?
C
C.
D E B
D. What else?
E B
E.
and B.
E and also B. Okay, all right. So how many character? One, two, three, four, five, six. Is it six?
E,
Six.
sir.
Can you E? Okay, seven.
Sir.
Anything else we have? We have a G, all right. We have G, F. Okay. We have A, C, D, E. We already have. Let's say here is B, and the last one is C. Right? Is it correct? Okay. Right. So to make sure for your human reading here, so we can try to sort the character here. Okay, we can sort it like A, B, C, D, E, F, and G. So we just remove this one. Okay, so make sure that the character exists in the message here. Okay, so basically here, so how many we call it as how many bits that we have if we have these messages here, right? So based on this one, okay, based on this one, we have 20 character, okay, 20 characters. I just make it like this, 20 characters. And remember that during your data communications is 1 byte, okay, is equal to 8 bits. Okay, remember this one, it's very important because one single character is equal to 8 bit because we can represent into like this one. One, two, three, okay, 4, 5, 6, 7, 8 in order to represent an ASCII code. Okay, right? So imagine that we have this message. Okay, so how many bits that we have here? If we have one character is equal to 8 bit and we have a total of 20 characters. So we have 20 multiplied by 8, which is equal to 160 bits. Okay, so we know that it's only just 160 bits. Yes, of course, because we only have 20 character. Imagine that we have a file that have 1 GB, and then we multiply by 8 bits. Okay, and then we transfer this file into your network by using the internet connectivity. Okay, so that's why the purpose of the the compressions algorithm, for example, by using a Huffman coding here to help a better transmissions here. Okay, so this one is just example how the process of the Huffman. Okay, so next step is we already identify the unique S key from this one. Okay, we have a 7. Okay, so based on the 7 here, we have a character, and then we need to identify, we need to count the frequency of each of the unique character. Okay, so we have A. How many A we have here? Can you count it for me? How many A? We have 1,
four,
2, 3, 4. So we have 4. Right? So we have 4 here. Then continue again like this one. So B, how many B? We have 1, 2. We have 2, right? Then we have 2. C, 1, 2, 3, 4. Is it 4? 4. D, 1, 2, 2 only. Okay. So E, what is here? How many E we have here? 1, 2, 3. E is 3. So F, how many F here? 1, 2. E is 4. Right. Okay. E is 4. Thank you. So F here is 2. Sorry for my bad writing here. G is only 2 as well. Okay. So can you verify the frequency of this character here? Just state it like this one, right? So I think that you can see basically like we have a 4, 2, 4, 2, 4, 2, 2. Okay, so we don't have any 3, 5, 6 here. So we count again, G is 1. Okay, so G is, sorry, G is 1. Okay, we have E is, okay, we can try to count it again. So A here is 1, 2, 3, 4. Okay, 4. B here is 1, 2. C is 1, 2, 3, 4. Right, it's 4. G is 1, 2. Okay, 2. E here is 1, 2, 3, 4. Right, okay. F is 2. G is, okay, G is 2 as well. Okay. Okay. So we already identified the frequency of the character here from the message that we have here is 20 messages. Okay, sorry, it's a 20 character in one message. And then we need to count what you call it, the code for this one. Okay, the last one here is the code. And remember that you need to refer back on the slide. Okay, how we can code. Okay, means that we encode again instead of 160 bit. Okay, by using the 8 bit for each of the character. So we can encode it again, right, by reducing the number of the bits here. All right. So right now we have, okay, we have only 7 character here. Okay, it's okay. 7 unique character from this one. Okay, it's a unique one. Okay, it's not counted as a what you call the multiple of the same character, but we want to know that the total size of the message before we do the Huffman coding. Okay, right. So the code here, imagine that we have a 7 here, right? Okay, how we can to encode it? Okay, is it only 2 bytes? Sorry, is it 2 bits? Is it, we can use 4 bits, or we can use what do you call last one here? Sorry, this one is 3 bits. Sorry. Okay, and then you can use 2 to the power of 1 is equal to Okay, 2 to the power of 2 is equal to 4, or 2 to the power of 3 is equal to 8. Okay, so this one is referred to uh, 0 and 1. Okay, this one is only 0 and 1 only, right? This one is referred to 0, 0, 0, 1, 1, 0, and 1, 1. And the last one here is referred to the 3 bits. 3 bits is equal to 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1. So we have 1, 2, 3, 4, 5, 6, 7, 8. Yeah, right? So since we have a 7 character here, okay, we must use to the power of 3, okay, that have only 3 bits that can cover 7 character. Okay, so you need to use this one, right? Okay, so we need to encode is with the new code, okay, by using only 3 bits. So this one will be 0, 0, 1, 0, 0, 1, sorry, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0, 0, 1, 0, 0, 1, 1, 1, 0, 0, is it? 1, 0, 1, 1, 1, 0. Okay, so you have this, okay, so you have this kind of a code for each of the character, and then we have a frequency for it. Okay, we have a character, we have a frequency, and then we have a code for this one. And this one is not stop this step yet, because we have a further step that you need to do, right? So it's step for this one. So you can count the original ASCII code. So we have original ASCII code, okay, is equal to 7 character. This one, 7 character is multiplied by 8 bits. Okay, before we do the encoding here is equal to 56 bits. Okay, right? So the new code, okay, so the new code is based on the 3 bits. Okay, 3 bits is equal to number for characters 7 multiplied by 3 bits is equal to 21 bits, right? So it looks like we already reduced some kind of the original 150 bits into more smaller parts here. Okay, so the size of reference, okay, reference. So what is the purpose of reference here? Because later on we need to do some encoding and decode back, okay? So let's say you transfer a file that already compressed, and the receiving machines need to understand how to decode again into the original file. Okay, so that's why we need to have some calculations for the size of reference. So right now, your size of reference here, we need to have an original ASCII code and also the new code, 56 plus by 21 bits, okay, is equal to 77 bits. Okay, right? So right now, can you understand until this one? Okay.
Yeah.
If you don't understand, you can watch this video again, right? Until at the end of the session today. So the next step here is we have a size of message, okay, which is instead of using 8 bit, we can use only 3 bits, which is that the total of the characters in the message is 20, okay, multiplied by 3 bits, okay, is equal to 60 bits. Okay, and the last part here is the total size of message. Okay, so what is the size of the total message here is this one. You need to count the size of reference together with the size of message. Like I mentioned just now, why we need to have the size of reference here. So the receiving machine need to understand how to decode again. Okay, how to decode again. And the size of the reference is set 57 and the size of message is 60. Okay, so whenever we count again, 77 plus 60. Okay, 61 is both of it is a bit is equal 137 bits. Okay, now if we compare with the original, this one to this one, okay, we have 160 versus 137 bits. Which one is the compressed versions? So of course the compressed version is this one, right? Okay, okay, so this question is not stopped here. Okay, it's not stopped until here. So there is a further steps that we need to cover in terms of the order of the frequency. We can reduce the numbers of the bits here instead of 137 into a smaller. Okay, it's into a smaller bits. So how we can design it one, right? So how we can design it one? So just now we have a character A, B, C, D, E, F, G. Okay, and imagine that this one is a what do you call example. I don't want to use this example. Otherwise, I give you a direct answer for this one. Assume that after we do this kind of this table just now, okay, this one, okay. So we have a frequency of the character, unique character. So this one is how the Huffman code works. Okay. Step number one here is you need to arrange the order of the frequency in the increasing order. Okay. So you need to arrange the frequency in order. Okay. So assume that in order here we have 2, 4, 2, 4, 2, 2. You need to arrange this one. Okay, which one comes first? Imagine that we have a this character. Frequency is 2, 3, 4, 5, 6, and the character that we have here is E, A, D, B, and also C. And this one is not reflect to the question in the above here, just to give you some example. Okay, some example. So we already arrange the frequency of the character here in order. Okay, starting from the smallest one to the largest number. Okay, largest number of the frequency. Okay, step number 2 here. We need to merge eh, two smallest node. Okay, and make it one node only. Okay, for example, in this one here, we have E, which is the frequency is 2. 3 is A, 4 is D, 5 is B, and the last one 6 is C. Okay, so what we can do here, we need to combine it. Okay, we need to merge the two smallest node. So two smallest node that we have here is 2 and 3. So this one will be merged first, so it will become 5. All right, so become 5. So right now, compared to the 5, 4, 5, and 6 here, 5 and a 4 here is the smallest one. All right, okay, so we can merge it together with this one, 4, and also 5, in order to get a new node. It's 9. Okay, it's 9. So comparing to the 9, 5, and 6 here, which nodes that have a smallest frequency? So 5 and also 6, right? Okay, so we need to merge this one first, so it become 11. So since we only have two nodes here, 9 and also 11, so we count it together as one node. It's become like a root of a tree. Okay, so step number 3, just now here we already done, since we need to repeat. Okay, repeat step in 2 again until we finish combining all together. Okay, we are combining all together. So so how we can count the bit that we have here? Okay, so we need to mark down. Okay, so we need to mark down all the left side of the node here is 0. So means that this part, okay, this part will become 0, this part will become 0, and this part becomes 0, and this part will become 1. Okay, this part will become 1. Okay, instead this one will become 0 as well. So 0, 0, 0. Okay, this one is 1, 1, 1, 1, and this one is 0. So what is purpose of we mark 0 and 1 in the, this one will be left side and this one is the right side? Here is we want to create a new encoding. Okay, so that's why we have a step number 4 here. We mark 0 on the left edges. Okay, where is the edge? Left side here. So this one here, this one, and also this one is the left edges. Okay, and mark 1 for the right edges. Okay, so just now we already marked the edges. We have a 0, 0, 0, 1, 1, 1, and 1 as well. Okay, so back to the table that we have just now. Okay, we have this one, this table, and we have the what we call the encoding here from this part. So we need to create a table, another table here. It's just like this one. Need to have a character. Then we need to have a frequency. The new code. Basically, this new code is come from this part. Okay. Okay, this part. And the message byte. Okay, sorry, a message bit. Okay, what is this message bits for each character? Okay, so we have character A, B, C, D, E. For example, we reflect to this one. Okay, and then the frequency of this one is 3, 5, 6, 4, and 2. So the new encoding here, okay, so the new encoding here is basically come from the nodes of this tree. Okay, so A here, the frequency is 3. So where is A? Okay, so where is A? So A here is this one. So how we can encode for A? We need to encode starting from the nodes here. Okay, starting from this one, 0, okay, 0, and we are reaching to the A is 1. So we type down is a 0, 0, 1. So for character B, so character B is here. So we need to start from this one, okay, 1, okay, and then 0. So we write down here is 1, 0. Okay, we don't have any 3 bits here. We only have 2 bits in order to encode the character B. Okay, so the next step here is C. So C, the same steps, we need to start from here as well. Okay, 1 and also 1. Only 2 bits. Okay, so can you see that the numbers of bits is already reduced? Okay, if we compare to the first step here, which is only 3 bits. Okay, all of the character is 3 bits. Okay, and then we can reduce it until only true and also 3 bits. So character D, okay, so what is the character D? Is this one. Okay, so the same step is 1, okay, sorry, 0 and also 1, 0, 1. And the last character is C. Sorry, the last character is E. Okay, and in order to traverse to the E nodes here is 0, 0, and also 0. So 0, 0, 0. So once you already have a new, okay, it's a new code here. So we can count the message bit for each of the character. Okay, so now is the last step here. We need to count each of the character message bits. Okay, I want to have here, let's say, how many bits we have here for the code character A. So we have 1, 2, 3. So we only have one, and we have only one. Sorry, how many frequency we have? Three. Three frequency for the character A is multiple by how many bits? Is 001 is equal to 3 bits. Okay, 3 bits. Then is equal to 9 bits. Okay. Now, so similar to the rest of the character here, character B, C, D, E, and each of the character may have different message bits size. Okay, for example, this one, we have 5 frequency of character B, then multiple by the numbers of bits for the code, new code here is only 2. 1, 2. 2 bit is equal to 10 bits. Okay, now the next step here is 6 frequency for character C. Okay, with 6 multiplied by only 2 bits, 1 and 2. Okay, don't read this one as a 11, 10, 1, 1, 0, right? Because we are using a binary here, 0 and 1 is equal to 12 bits. This one is 4 multiplied by 2 bits is equal to 8 bits. Okay, and the last one here is 2 multiplied by 3 bits is equal to 6 bits. Okay. Okay, so you need to count all the message bit. This one is total of the message bit is 9 plus 10 plus 12 plus 8 plus 6 is equal to something. Okay, let's say you got some this number. Okay, and then you need to count all of it, this one as well. So until you got for the last output. Okay, so this is the part of it, and you need to continue for this part in order to get the message bit, the size of message bits. Okay, it's not only this one. There is some calculation that you need to do here, and also some calculation that you need to do here. Okay, so you need to watch over on the instruction given by data scientist as well. Okay, so the second part here, you need to find out the code that implement the Huffman coding. The output of your code must similar with number one. Okay, whatever we have doing all together in here, all right, so you will get the same output by using the coding. So the first step here is manual. Okay, manual process. Okay, step number two here, okay, sorry, is question number two here is automation by using a coding. And the last one here, you need to analyze your answer by providing the following statement. So how much the Huffman code able to reduce the message? So how much instead of 160 bits? Okay, and we implement Huffman code. Okay, let's say it's reduced only 100 bits instead of 160. For example, okay. So how many percent? So we can say that is 100 bit by this one is 100, and then you got the percentage of reductions. Okay. So how efficient gradient methods in the Huffman code, and then this one you need to find out. And of course, the last part here, you need to find the complexity of the code. All right, the big O either is something this one, okay, or like this one and so on. So you need to find out. Okay. All right. So I want to share you something here that is very useful for you. And you can try to Google in other website as well instead of this website. And you can try to find out in the programease.com website. Okay, and you can go through for the Huffman coding. It's very useful for your understanding as well. Okay, they given you step-by-step process how to encode the character, okay, by using the Huffman coding. Okay, and this website gives you some example how you can encode. Okay, let's say for this example we have our original ASCII message size is 120, so we can reduce it until 75. So imagine that we have doing this one just now, okay, and you need to count the frequency as a bits as well, and the character we have just now we have how many characters? 7. Okay, 7 multiplied by 8 is equal to something, and you need to count all together. Okay, and the sample of the code here given here, and the sample of code by using the structure. Okay, hopefully you still remember how to use structure in your program, okay, especially in the C programming. Right? Okay, so that's all for briefing for today.